Everyone. I'm very happy to be here today and share the results of my study. And the title is Application of Seismic Attributes and Machine Learning Techniques to the Characterization of Faults in a Post-Salt Reservoir, Jubarte Field, Campos Basin. Dr. Vito is my advisor, and the committee is composed by Dr. Carpenter and Dr. Prenter. This is the main outline that I'm going to follow in the next 30 minutes. With the main topics, I will start with the motivation. And we are geoscientists, and we know that we can have different types of faults that are going to be controlled by different parameters, for example, composition of the rocks, change in the stress system. So we may have a major fault surface, as we can see here with this figure, or we may have a broader deformation zone with more discontinuities as indicated with this image. And we can expect the same variability in the subsurface. Here we are looking at my study area in a time slice. So we have seismic data with some abrupt change in the amplitude. And if we look in a cross section, we can see also some change in the depth of the reflectors, change in the amplitude continuation, some small offsets that helped us to see its continuities. In some cases, it's easy to see that feature, but in other cases, for example, for fault number 2, if you look in a time slice, it's more difficult to be sure about the interpretation if we can have some more questions. And working with seismic, we may have some additional ingredients, for example, the presence of seismic noise. Here we have some cross-cutting events that makes our interpretation a little bit more difficult. Also, we have this interval that has a weak impedance contrast, for example, compared to the reservoir. So I consider this a more critical interval. And these examples of difficulties motivated me to look for alternatives to what attributes can be applied and additional techniques that I can use to improve the recognition of faults. And in the literature, we have many examples of features that we can use to highlight faults. For example, offset reflections, changes in depth, variations in the signal noise and the amplitude phase components. And looking again the study area, in some cases, it's more easy to see discontinuities. But on the other hand, here I have one example of a subtle variation, as you can see. And we have more uncertainties if we are going to stop our interpretation in this point or if we can extrapolate until this region. Again, another example of the complexity involved. And so I have this major question, how we can improve the identification of faults. And by only looking the attributes response, for example, this image, I have the amplitude combined with the similarity attribute, and we can see some faults, discontinuities, some surface like here and also in this region. But we're also going to emphasize, for example, chaotic deposits, so stratigraphic features, and also seismic noise. And for this interval in specific, I have, for example, here the NRMS error. So I use 2 volumes from 2 different surveys. And I compare the RMS and get, for example, 7% of difference. That is higher than the average value described for other intervals and for other parts of the volume. So this is another way to see the impact of the noise, a more quantitative way. And I decided to break this major objective into minor questions. For example, what methods can be applied during the data preparation? What seismic attributes are more appropriated? Is it better to use the full amplitude spectrum or specific frequencies range? In addition, if we consider the impact of different azimuths, what observations can we obtain? And finally, considering the different numbers of inputs and different types of attributes that I tested, I used the PCA and SUM, 2 unsupervised machine learning techniques, to see if I can get additional insights for the interpretation. Now I will briefly describe the study area. So we are in the northern part of the Campos Basin, about 77 kilometers offshore the Espírito Santo State coast. And here we have a summary of the evolution of the basin. We can identify 3 main sequences. We have the non-marine sequence here with many faults associated with the breakup of the Gondwana. Then we have the deposition of the salt units here during the transitional sequence. And later, more recently, we have the marine sequence. And during this time, we have the deposition of important turbidites that are going to form reservoirs. And one important takeaway of this slide, as you can see, we have faults here associated with movements of salt, and they're going to control the position of the reservoirs and also the hydrocarbon distribution. And we are going to focus on the Maastrichtian interval. It's located in the drift stage of the evolution. And here we have the two main formations, the Campos formations that contain the reservoirs, and the Ubatuba that includes the adjacent units. And the characterization of this discontinuity is important for regional studies, but also for applied investigations. Here we have Jubarte Field, and we can see that the eastern termination of the field has this major fault. And the characterization of these elements will be important because it will help us to extrapolate porosity, permeabilities, and other properties during the management of the field. And more related to the geophysics aspects, we have some publications that describe the AVO response, how they vary over time. So the 4D aspect of the anomalies, how they change close to producer and injector wells, they have different signatures. And also we have an idea about the different impact of saturation and pressure. We also have works that describe the impact of this change in amplitude and how they can be associated with properties, so seismic inversion analysis. But today I'm going to focus on the use of attributes to highlight faults and how we can use some additional techniques. To do that, I will just briefly mention some important concepts related to the attributes. For instance, we have different classes of attributes that can be applied. For my study, I decided to work with the instantaneous and the geometric, and here are examples of attributes that I tested. I did more analysis with the geometric class. Here are example of attributes. We are going to see in the results. I tested different parameters to see the impact of that. And I will describe some key concepts related to the attributes now. The first one is the importance of working with the complex seismic trace. So the seismic data that we acquire in the field is composed by this real component, as we can see here with this representation. It is defined by an amplitude and phase terms. And if we apply the quadrature operator, for example, we can have the imaginary part that it's also going to be defined by amplitude and phase. And in conjunction, these two components will give us more alternatives to compute the attributes. And also in many situations, they are going to improve the results. And looking in more detail the instantaneous, I will show two examples of attributes that can be applied for identified change in the lateral continuation of the reflectors. The instantaneous phase is one of them, defined by this relation of the imaginary real parts. And also we have the amplitude volume transform, another example of attribute. And as you can see with this figure from Bulhões and Amorim, we have the original seismic data in a time slice. And here we can see more easily these discontinuities. More related to the geometric class of attributes, we have a different approach that can be used. Here we have the coherence type of attributes using cross-correlation. So the idea here, we are going to apply different time lags between adjacent trace to see similarities and regions that can indicate faults, for example, lower similarity anomalies. We also have the semblance-based approach. Here we have maybe more control, more parameters. We are going to work with different types of windows, elliptical or rectangular. And we are going to include more informations and also more vertical samples. And one important aspect we are going to emphasize, or we are going to correct the effect of the dipping of the reflectors. That will be important to emphasize the features that we want to see, in my case, faults and fractures. Other example of attributes that I evaluated is the curvature that describe change in the shape of the reflectors. So here we have, for example, a subtle variation in one surface. And if I compute the first derivative, I will have dip. The second will provide me the curvature, and the aberrancy is obtained by the third derivative. So these are examples of different response that we can have for this change here and how it's important to get familiar with these techniques. For curvature, we may have different components that we can use to see the response. I will just focus on the K1 and K2 that correspond to the most positive principal curvature component and most negative. And in summary, they're going to reveal chains, for example, associated with small anticlines. So these are considered more positive anomalies. And here can be described as a negative curvature. The PCA, I use it to identify volumes with higher variability. This technique can be applied in different moments of the workflow. I use it after the computation of the attributes, like some publications. And after doing this type of analysis, I selected some of these attributes to use in a self-organizing map. So we are going to use these unsupervised clustering techniques to see if we can identify features of interest. Let's say if we can see faults and fracture using this technique. And for the data and methods, I use it basically Jubarte PRM project. It's a 4D acquisition, very modern techniques. For example, we have optical fibers with receivers located in the seafloor. We have here some information. For example, the final migration grid is 12.5 by 12.5. The algorithm used was the VTI Kirchhoff depth migration. That's very important because I can have more confidence about the position of the anomalies. And looking the amplitude spectrum, in the beginning, I compared the PS wave response, the volume, with the PP wave data. And as you can see, I have a broader amplitude spectrum with this type of data. So that's why I decided to work basically with these components. And considering the dominant frequency that we can have here, this range, and also possible variations of the velocity close to this interval, a representative value for the vertical resolution is about 25 meters, but it can vary a little bit less or more. And another important source of information are the wells. I use it especially for wells to do the well tie and create some synthetic seismograms to calibrate the investigation. So here we have, for example, the top of Cretaceous response with a strong impedance, a regional marker, and the response of the reservoir. These are complementary techniques. And as I mentioned in the beginning, for the workflow, in my case, the presence of noise and intervals with weak contrast of impedance are critical elements. That's why I included a spectral balancing phase to improve the lateral continuations of some reflectors, especially increasing the higher frequency. And also I applied the structure-oriented filtering. It's another technique to attenuate that random noise that I mentioned in the beginning. I received great suggestions and comments from our group, from Dr. Marford, and also I have here one example of publication that described the importance to have these two components and also keeping this order to have a better response. And so I have these three main phases: data conditioning with the spectral balancing, structure-oriented filter. Then I have the attributes computation phase, when I have the instantaneous and geometric classes with different algorithms, with different parameters that I will show in a minute. And finally, the unsupervised machine learning part, applied to also look for alternatives to improve the identification of faults. Now let's see the results. I have here a vertical section, my initial data set, and we can see that after the data preparation, I can better delineate some reflectors indicated here with the green arrows. In the beginning, the difference are not so clearly, but now after doing this process, I see improvements also for the identification of these discontinuities. Here, the difference is small. It's also difficult to see, but there are some more clear limits for the anomalies, and that's important for faults. I cannot use this output for other studies, for example, AVO inversion, because I changed the amplitude, but for the identification of faults, I see improvements. And after doing this step, I computed the instantaneous attributes. Here are some examples. We have a vertical section with my original seismic data. We have these two discontinuities, and comparing with this different response, I will, for example, emphasize that envelope and the RMS helped me to see, in some case, some change in the amplitude, but they are limited for intervals with strong contrast of amplitude. As you can see here, it's difficult to get insightful observations. We have this nice visualization of the amplitude volume transform that also helped to see some internal variations, for example, here in this region, but it's also going to be impacted by some vertical components, some features that we can see here. And the cosine of instantaneous phase, it's another interesting attribute because it's not impacted by change in the amplitude. As we can see here, these different contrasts, they are not so strong here. And we have a very sharp limit for these discontinuities. So it's an important aspect. When we look in more detail, another section, again, we have these subtle variations here in this region, the response of the amplitude volume transform, the cosine of instantaneous phase giving me this anomaly. But what I also want to emphasize that we cannot use only one attribute. For example, the cosine of instantaneous phase that has this nice visualization in a vertical section, when we see in a time slice, like here, close to the edge of the survey, we are going to emphasize noise. So these different attributes, each one have some pros and cons, but the cosine of instantaneous phase is a good attribute, especially when we are going to work really focused on the reservoir in the area of interest. Now let's see the geometric. So I tested different algorithms, and the curvature, structural curvature provided me more uniform anomalies, as we can see here with the K1 and K2, so the most positive and most negative anomalies. They are better to have a big picture analysis of the area. Here we are going to have major anomalies with the long wavelength. So it's one type of filter that I applied compared to the short wavelength when we can see more detailed features. Let's look in more detail these two parameters. Here we have a time slice. And one important aspect, for example, if we look the anomalies here indicated in blue, so the most negative anomalies, they are associated with the hanging wall part of this fault. And it's interesting because only by looking at time slice, we can have an idea about the geometry of the fault, in which direction we can see the deepening of the structure. Of course, we need to check in a vertical section, but it's one example of a combination of the methods. And another takeaway of this slide is the fact that not all the anomalies here are revealing faults. Here I have one example of a stratigraphic termination of a reflector with this smooth anticline. So this is a stratigraphic termination that's also going to be emphasized the geological meaning of the anomalies. These two curvature components, again, with short and long wavelength, we can see here for the reservoir, especially in these regions where the faults or discontinuities are vertical, association with the anomalies, short wavelength ondulation, as we can see here, so can be impacted at some point by problems in velocity, let's say like that, and also by the presence of noise. For example, here in this reservoir, we are going to emphasize the noise because of this parameter. If we look the long wavelength parameter, we are going to combine at this region, these small anomalies, we are going to see like a major response like this one. And we are going to be less sensitive for the noise, but when we are going to have features or faults with different dips, not vertical, we can see some artifacts. For example, here we have these star step features that are not exactly the geometry that we are expecting to see. It's one example of limitation. And the other geometric attributes that I evaluated, the Sobel filter, we are looking the response of Sobel filter and also the energy ratio. And we can see that the energy ratio provided more sharp defined anomalies. So the contrast is easy to identify here. I used the same limit for the two figures. So I consider this the best attribute to use. Also looking in a time slice, we have here a comparison with the original amplitude volume. And you can see, for example, here we have a better definition of this structure compared to the Sobel filter. Also in this position, the anomaly is better focused compared to here, that it's a little bit more blurred. And in general, we can complement analysis locally with Sobel filter. For example, here are two examples of improvements that we may obtain with this attribute. And we also were able to see some curvilinear features that may represent channels. So it's important not only for identification of faults, but different types of channels, limits, or edges. And after deciding to work with energy ratio in more detail, I did 2 more investigations. This is the result of the frequency. So we have the original amplitude volume, and here I used the broadband volume to compute energy ratio. And as you can see, we have less noise. We can see this structure. If we only look at the lower frequency, we are going to see just part of the anomaly. For this interval that I was more focused, I couldn't see too much improvement. So it's limited potential. And also here, by only looking to the higher frequency, we can see the strong impact of the noise. So that's why I consider the broadband a good input to delineate the faults. And also this work we submitted as an expanded abstract to the SEG, but we can see here the impact of using the full stack azimuths. So I'm including here with this upper part, this time slice, all the acquisitions orientations, and we have less noise in this case, and also we can see more uniform anomalies indicated here with the yellow arrows. Compare this region, for example, here it's more rectilinear and also uniform. We have a more continuous response. For example, here we have some gaps, and also in this region. But we can obtain some local improvements using these specific orientations of the acquisition, these specific azimuths. That's what I'm trying to show here. We have a 3D visualization of this structure. And using the full stack, we have a gap in the feature. And when we use the acquisition that was acquired perpendicular to this anomaly, we can see a better extension. So it's one example of improvement. And that's why I consider that it's important to do a first interpretation with the full stack and then use these specific acquisitions oriented perpendicular to have some additional insights. The PCA, I got better response with the geometric class, and this slide shows one example of exercise that I did. I used these 3 attributes having different inputs, the multispectral, the broadband, and different frequencies filter banks that I'm showing here. So each of one of these, I use it as one input. And after doing the PCA, we are going to be able to highlight the volumes with the higher variability. Here I have the first principal component. And if you look the volumes that has strong contribution, we can see that are the multispectral and the broadband volumes, this first 6 volumes with the higher contribution. And this is in agreement with my observation that the broadband, for example, it's a good volume to recover the fault geometry, and it's probably associated with the higher amplitude content of these volumes, and they're going to reflect in good identification of faults. And after doing this type of exercise, I selected different attributes to use in self-organizing maps. And I noticed some improvements. Here I have one example. In a time slice using our amplitude volume, it's more difficult, for example, to see small contrasts here. And by using this technique, so now we have many attributes. And I decided, for example, as an user, we can define the number of clusters that we want to classify. And we can see better these subtle variations, for example, using an 8x8 topology. So in total, I have 64 clusters that were used to classify these attributes. And they are revealing this subtle variation here that could reflect a subtle fault. We have this small offset of this reflector, some interruptions here, and also a change in the amplitude at this region. So can represent a fault segment in this region. So I consider this a complementary technique because, as I mentioned, at the first moment, it's more difficult to see these subtle variations. Another example of improvement I have here with this image. And now I have a 10x10 classification here. And by only selecting these 2 clusters, I was able to identify these anomalies indicated in orange here. And in the reservoir, they correspond to a position of discontinuity, but also they're going to be impacted by noise, as for example here in this region, and also for this interval. So they can optimize the analysis, but we need to QC the results because as we are using attributes, they also going to be impacted by the presence of noise. Finally, for the discussion, I will quickly return to my initial questions. So what methods can be applied during the data preparation. I did initial analysis with the structure-oriented filtering, that it's a common technique to use for structural investigations in seismic, but I see improvements also using spectral balancing. So this workflow, for example, proposed followed by Tengha, it's a good approach to use. And for the most appropriate attributes, if we only consider the instantaneous attributes, the cosine of instantaneous phase and amplitude volume transform are good examples of attributes to be applied. But I got better response with the energy ratio similarity, more clear anomalies, and locally we can complement the studies, for example, using curvature, especially with short wavelength for the reservoir. That's what I'm trying to demonstrate here. So this multi-attribute, I see improvements. For example, here we have the similarity response for this horizon slice, and we have the anomaly, it stops here. And by using these two other components, the curvature, K1 and K2, we are able probably to extend the definition of this feature a little bit more laterally. So with this anomaly, we can see subtle variations of the reflector, and this demonstrates how the techniques can be complementary. For the fault geometry, I got better results with the broadband. And for this part, I saw in the literature many examples of publications where the authors describe improvement using different frequencies. But for the preliminary results that I got, I noticed better response with the broadband. So maybe if I have more time or do more analysis, we can obtain more insights. For the azimuth aspect, the full stack has less noise, and local refinements can be obtained when the acquisitions are oriented perpendicular to the discontinuity. So we have to have these basic characterizations to later use specific acquisitions. And PCA and SUM can complement the analysis, especially using geometric attributes. As I show, we can see some improvements. For the instantaneous class, I just got limited results. They are especially revealing stratigraphic features. And more recently, I saw some also limitations associated with these attributes as described by these publications regarding cyclical attributes, because we have some interruptions in the anomalies, for example, with the instantaneous phase, and that could represent non-desired features or issues during our PCA and SUM studies. These are the main conclusions. So I noticed the importance to have a data conditioning phase instead of just going directly to the computation of the attributes. It's important to have a first step to identify the critical aspects, for example, in my case, noise and intervals with weak contrasts of improperties. Then I was able to see better faults with higher contrasts. The better results I got using the geometric attributes. I noticed improvements using this multi-approach or multi-attribute approach. PCA and SUM, I consider complementary techniques. They are not supposed to replace our traditional approach to see faults using our original amplitude volume, but they can optimize the analysis. And considering the other applications of this type of study, I don't know, I didn't use production data, so I don't know how critical it is for Jubarte Field, but for other cases where we have some mature oil fields with a more structural traps, more evident with higher faults displacement, and this type of studies can complement the characterization of the elements. And here I have one example of publication that describe how critical it is to characterize faults, because we can change and modify the development strategy of a field. And for future work, I have one suggestion here. If I have, for example, well image logs to calibrate the response that I got with the attributes will be important. It's another quantification method to calibrate the response. These are the reference that I used during this presentation. And finally, I want to express my gratitude to Petrobras for the support and authorization to make my studies here at the University of Oklahoma.